Hello and welcome back. The topic of this video is the interaction of charged particles with matter. And if you look behind me, you'll see a great example of that. So this is the Aurora Borealis, or the Northern Lights. And you'll see these sometimes at night, especially near the North Pole as you get to northern latitudes. What's happening here is you've got charged particles from outer space. Those are electrons or protons that come from the sun. And they come down into the Earth's atmosphere. They interact with the atmosphere. They ionize atoms in the atmosphere. Those atoms then fluoresce down and give off light. A beautiful example of charged particle interaction with matter. So there are two main ways for medical applications that charged particles interact. So you've got one, they can lose energy through radiative loss, or they can lose energy through collisional loss. And I'm going to go over those two processes separately. This particular video I'm going to start with the radiative loss, and in the next video we'll talk about collisional losses. And then at the end we'll also talk about neutrons. They're not really charged particles, but I think it sort of fits in with this topic. All right, here we go. So we're going to start by considering an electron here in blue interacting with an atom. This is a minus charge. It moves in this direction, and it experiences a repulsion between the like charges. That's the Coulomb force between electrical charges. That force is given by the charge of one particle, charge of the other, divided by the distance squared, and some proportionality constant. This whole process is called collisional process, collisional energy loss. Now let's study the other process for a minute. So here's the atom again, an electron. So normally it might move in a line like this, a straight line. But it doesn't because there's a force on this particle. It's an attractive force because these are opposite charges. The nucleus and the electron attract each other. So it doesn't move in a straight line. Instead, it moves in a sort of a curve like this as it gets pulled by the force from the nucleus. That's an acceleration, because anything going through a curve experiences a force acceleration. So as it does that, it actually emits a photon, because accelerated charges emit photons. We'll look at that later. And this particular photon is called Bremsstrahlung radiation. That's a German word, means breaking radiation, acceleration. This whole process is called radiative energy loss. Before we look more closely, though, I have to introduce this concept of how energy loss is quantified. So we have an electron here, let's say. It's wandering around through matter, takes kind of a path like this. And as it does, it loses energy, delta E, over some length, delta X. It loses that energy through collisions or radiation. So I'm going to write it in differential form, minus the E dx. The minus sign because it's energy loss. So energy loss per unit length. The units of this are MeV per centimeter, or sometimes KeV per micron. And now you actually want an intrinsic quantity for this, and so what we're going to do is divide by density, and that takes out the density dependence, and have this quantity, energy loss per gram per centimeter squared. Okay, this is a special quantity. It has a special name, and it is called stopping power, S. And this is very important. So just spend a minute with this. Think it's just energy per unit length, basically. So now that we understand how stopping power is quantified on a macroscopic level, we can go back here to this microscopic level, and we can write an expression for the stopping power. So I'll write this as the total stopping power, S tot. It's going to equal the stopping power from the collisional process plus the stopping power from the radiative process. They're just additive. Sometimes this collisional stopping power is called the electronic stopping power, electronic S, because it's an electron process. And this one then, of course, is called the nuclear stopping power because it involves the nucleus. But those are just terms that you might need to know. We're going to study first the second term, the radiative stopping power, because it's a little bit easier to understand. So I'm going to write down some equations that will describe this radiative energy loss, or the Bremsstrahlung. So these are going to kind of rely on some freshman physics properties. So first of all, power is proportional to the acceleration squared. I'm writing proportional with this little alpha. That means proportional to. Also, you remember from freshman physics that the force between two charged particles is given by the Coulomb law, E times Z. So Z is the charge of the nucleus divided by the distance squared. And then you also remember Newton's law, F equals mass times acceleration. With these simple concepts, we can tie these things together. This is kind of the semi-classical approximation. So the stopping power is proportional, alpha is proportional to acceleration squared. That's just a fact I'm going to use. And acceleration squared is proportional to, if you solve for these equations, you can find out that it's the charge divided by the mass squared. That's just plugging in together. So this has several important implications. Number one, let's talk about protons. When protons interact with matter, the energy loss, stopping power, is pretty small. So why is that? Well, it's from the above equations. You can see the mass of the proton is large, so stopping power is small. Number two, for electrons, there's a couple properties that you can note. So first of all, this Bremsstrahlung loss, radiative loss, is important. And that's because the mass of the electron is small. Also, the Bremsstrahlung loss is larger in high Z materials. And there's really no need for you to memorize that or know the equations. It's really just intuitively obvious if you think about it. If you have a small particle like an electron, it gets whipped around the nucleus. It radiates a lot of energy off. It's accelerated a lot. If you've got a bigger nucleus, it gets whipped around harder, and so more energy is lost. And so it's really just kind of obvious if you think about it at an intuitive level. Okay, now let's look at what this looks like quantitatively. So here's the plot for these dependencies. What you're looking at is stopping power for electrons as a function of the electron energy. And so here's the Z dependence. And as you go from water to lead, as you raise the Z, the radiative stopping power goes way up. This is a log scale. And also, as you go up in energy of the electron, the stopping power goes up. And that sort of makes sense too, because you'll remember that stopping power out is proportional to the acceleration. And you have a higher energy, you have a higher acceleration. Good. So that finishes our discussion of radiative losses for charged particles. I'm going to leave you here with a little more background reading that you can study more if you like. In the next video, we're going to move on and talk about collisional losses from charged particles. Thank you.